The problem with traditional construction activities is that they rely on the use of heavy equipment which produce a lot of noise, exhaust, and CO2 emissions. Most heavy equipment that is used in construction is dependent on diesel fuel or gasoline to run. Most electric power that is produced on site is produced using generators that burn diesel or gasoline fuel. Electric motors are a viable substitute for gas and diesel motors, but powering electrical motors and electrical equipment requires high levels of electricity. The two current battery technologies we are focusing on for our research are lead-acid and lithium-ion batteries. Lead-acid batteries have been around since 1859 and were the first rechargeable battery for commercial use. The inherent problems once found have been virtually eliminated with new development. Lead-acid batteries are found in cars, small electric vehicles, electric scooters, and on-site solar storage. In construction, they are ideal for remote area power supply. Lead-acid batteries are so widely used because they provide a high current at a low cost. The problems with lead-acid batteries are there's potential danger with risk of exploding when recharged too many times or when short-circuited. There are also many environmental and health concerns. Approximately 40,000 metric tons of lead end up in landfills every year, and approximately 70,000 metric tons of lead are released during mining and manufacturing processes. Lithium-ion is the second most mature technology in the stationary battery energy storage market just after lead-acid. It was first proposed in 1970, released commercially in 1991, and is now the standard technology for portable electronics, electric vehicles, and stationary or portable energy storage. Lithium-ion batteries have large storage capacity, fast recharge capability, and much less environmental impact. They're safer and offer potential cost reduction. We've identified two potential high use cases and done some cost analysis. Heavy equipment such as loaders, dumpers, excavators, rollers, trucks, and skid steers are using hybrid systems and battery technology. The electrification of machines allows for greater efficiency. Software can decouple a machine's subsystems so that, for instance, hydraulics will not be dependent on engine speed. Hybrid equipment delivers a 20% fuel savings. Another potential use case is on-site storage of energy. If a site can run fully sufficient on battery-powered devices and equipment, it can potentially eliminate 40 to 60% of diesel fuel consumption on that site. The reliability of having on-site renewable energy can guarantee that construction will not be delayed due to fuel shortages or transportation issues. When looking at a SWOT analysis, some of the strengths of battery technology are that it is clean, requires low levels of maintenance, is reliable, and has no or low emissions. Some weaknesses of battery technology are that it is expensive and can be difficult to scale. Some opportunities with battery technology are that it is able to be paired with renewable energy production methods, such as solar, wind, and geothermal. New battery designs offer higher efficiency and smaller form factor, and portability is becoming easier. Some threats of battery technology include the material limitations and the geographic location of raw materials to mine. Also, batteries can be impacted by weather, and there are new technologies such as capacitors, supercapacitors, and fuel cells that may offer more storage in a better form factor. In conclusion, we have found that there are many opportunities for using battery technology as an alternative to traditional fuel sources on construction sites. When paired with other hybrid technologies, battery technologies make sense. Current battery technologies are relatively stable and do address many of the problems that we have identified, such as pollution on site, CO2 emissions, and on-site storage challenges with respect to energy.